Alright, here we go, taking notes on section 6.5, talking mainly about the trapezoidal. Going over some quick review questions on concave up and concave down. I'm assuming you're remembering that it takes the second derivative to be positive if it's concave up and the second derivative to be negative if it's concave down. Go ahead and push pause and take a couple minutes to see how many of these you can figure out. So what we're covering today in our notes is the trapezoidal approximations. Isn't that a fun word? Maybe one other algorithm for the Simpson's rule, which we mentioned a little bit today, and I don't think we'll get to error analysis. So here's a picture just demonstrating how the trapezoid rule works. Remember, our just general formula for a trapezoid looks like this. The area is 1/2 the base. Actually, we usually call that the height. Times base 1 plus base 2. So 1/2 this distance, we'll call that h, in our general formula, then times the quantity base 1 plus base 2. So really what that is doing is finding an average of the lengths of those two sides of the trapezoid or the base and then multiplying it by your height. So it's finding the rectangle that would be equivalent to that trapezoid. So when you do that, you're using this particular height, that y1 right there, twice. You're using it once for this trapezoid that's in red and once for this trapezoid that's in blue. So you're going to be using each of those side lengths 2 different times, except for this one, which is only used once, and this one, which is only used once. But each other one is going to be used in 2 different trapezoids, one to the left of it and one to the right of it. So after you write all of the areas of those individual trapezoids, factor out your h, you are left with formula right here. This is the trapezoidal rule, the formula that you use to find the approximation. Looks like our parentheses didn't make it in there, hopefully they're on yours. This is the approximation of the area under the curve or the integral, because it does make it negative. Using trapezoids instead of rectangles. Notice h, we'd probably say b minus a all over n, so that's your 2 endpoints. Notice limits of integration from a to b, divided by n, the number of subintervals that we have. So if there's 5 subintervals or 6 subintervals, how many trapezoids you want to put into that graph. So what that really is doing is just taking the left-hand Riemann sum and the right-hand Riemann sum and averaging them together. So it's not quite the midpoint Riemann sum, but it's the left plus the right divided by 2. Interesting that that gives you the same answer. So the trapezoidal rule is the same thing as taking the left Riemann sum, the right Riemann sum, and dividing it by 2. Which leads us to Simpson's rule. Put my parentheses in here again. Again, I'm not going to prove it, but I did notice that there is a little walk you through proof in the book if you're interested. It says this: you take your h, which is the height, again, you take your intervals divided by the number of subintervals, and divide it by 3. And then you take your first height plus 4 times your second plus 2 times your third, 4 times your fourth, and on, rotating back and forth between 4 and 2 and 4 and 2 until you get to the second to the last one needs to be a 4, and then your last one is times 1 again. Since it has that pattern in there, you do need to make sure with Simpson's rule that you are using an even number of subintervals. It does not work for an odd number of subintervals. Alright, my bell's about to ring here in a couple minutes, so before people think I'm totally crazy talking to myself, let me try to get a quick example done. What if you wanted to use 4 subintervals to approximate the area from 0 to 2 of x squared dx using the trapezoid rule? Alright, well, my trapezoid rule says you take the height of each interval. You're going to find that by taking b minus a all over n. So that's 1/2. So we take our 1/2 divided by 2 times the heights at the different intervals. Let me go ahead and calculate that. So our height at 0 is 0, plus 2 times our height at 1/2, 1/2 squared is 1/4, plus 2 times our height at 1, 1 squared is 1, plus 2 times our height at 1.5, which is 9/4, plus our final height at 2, 2 squared is 4. So we calculate that. Alright, so as you simplify that, you get 1/4 times 11, and 1/4 times 11 is 2.75. So I get 2.75 as my answer. The question I want you to be able to answer about that when we come to class tomorrow, is that going to be an overestimate or is that an underestimate? Alright, I'll get one more example on here and then we'll call it quits. So here we have a problem where we're using the trapezoid rule with 6 intervals, but I don't know the function. I just know that these are the values of the function from 0 to 6. So my goal is to find the integral from 0 to 6 of f of x dx approximately by using this trapezoid rule. So my trapezoid rule says that I take the width of the interval divided by 2. The width of each of my intervals is 1. You could have also done 6 minus 0 divided by 6 to get your 1. So I take 1 divided by 2 times my first height plus 2 times all of my other heights. 2 times 10, 2 times 9, etc. Plus only 1 times my last height of 18. I simplify all of that and multiply, and that will be my approximation of this integral. Before you come to class tomorrow, I would like you to look at page 316, problem number 10. It's a problem about stocking a fish pond. I want you to answer part A and part B if possible, and if not, come with questions as to why you couldn't do it. So I hope you have a good night, and we'll see you tomorrow.